Hello everyone, I'm Leo from CIMAP Laboratory in Grenoble, France, and today I will present to you the effect of Icosahedral short-range order in the liquid on the microstructure of an austenitic stainless steel generated from L-PBF. I know that all of you know what Icosahedral short-range order is, but do not worry, I will explain it further in my presentation, and we will see that this can induce a solidification mechanism that leads to positive microstructure change, such as grain refinement and texture randomization. I would like to first to thank EDF for funding my PhD. To begin, we wanted to study the influence of chemical composition inside the Swiss 16L standard. To do so, two Swiss 16L steels were manufactured by L-PBF from two different powder batches. So we have the first powder batch comes from SLM solution, and the second powder batch comes from Praxair. And so they are elaborated under the same manufacturing condition, and so we obtain two steels, the SLM steel and the Praxair steel. At the table at the right, you can see the chemical composition of the two steels, and what is different. Both steels respect the Swiss 16L standard, but what is different, the main difference, is the nitrogen content. In the SLM steel, there is high nitrogen content because the SLM powder have been atomized by nitrogen, while in the Praxair steel, there is low nitrogen content because it is atomized by argon. So at this point, we will characterize the microstructure and expect closed microstructure because it has a closed chemical difference. But we will see this is not the case. So here, in this are the IPF EBSD map of the two steels. So we can see that it's quite different. The SLM steel have bigger grain than the Praxair steel. So from a change of powder composition, we obtain a refinement of the grain size. We also obtain a less pronounced texture, as you can see on the 114 figure at the bottom, where you can see the SN have a quite relatively big texture with an intensity of 4. That is quite common in this kind of steel, while the Praxair steel have a low texture. And so from change in powder composition, we obtain also a less pronounced texture. But what is the most different between the two steels is the twin boundary fraction. As one can see on this grain boundary map, where in black is plotted the grain is a classic grain boundary, and in red the twin boundaries. And so in the SLM steel, there is a very low fraction of twin boundaries, around 1%, which is very close from the random value. While in the Praxair steel, there is a lot of twin boundaries, around 30%, which is way above the random value. And so this kind of Praxair microstructure with a lot of twin in the as fabricated state is not highlighted in the literature and can be interesting because we show that it has a lower texture, so we expect lower anisotropy in mechanical property. So we will try to do some hypotheses to find the origin of this special microstructure. The first hypothesis we made was that the thermomechanical treatment can modify the microstructure. So it is well known that all L-PBF material undergo thermomechanical treatment or solid state thermal cycling during L-PBF, and this could induce a change in the microstructure. So this hypothesis could explain the refinement of the grain size, and can also explain the presence of twin boundaries, because it is well known that an austenitic stainless steel, after thermomechanical treatment, creates twin boundaries. So to validate this hypothesis, we will observe the microstructure of areas. There are no thermomechanical treatment occurred, and we expect a different microstructure than the core materials. So the first area we observe is the last layer of the Praxair steel, and we can see that inside the last maple we still see a lot of twin boundaries. So this is quite unexpected with this hypothesis. The second area where no thermomechanical treatment occurs is the study of the initial Praxair powder, where one can see there are still a lot of twin boundaries plotted in gray in the grain boundary map, and there is still around 30% of twin boundaries, so close to the value of the Praxair steel. Why? We can see also that the powder have a solidification microstructure with dendrite. And so the hypothesis of annealing twin or twin created by the thermomechanical treatment is not really convincing. And we need an hypothesis to explain the creation of twin boundaries during the solidification. This hypothesis is icosahedral short-range order, or ISRO, mediated nucleation. So this is a mechanism proposed by Pro-Tudu and Rapad to explain the grain refinement and high twin boundary fraction in a cast aluminium alloy with the addition of 0.1% of chromium. This hypothesis has been also involved to explain the grain refinement and a lot of twin boundaries in the gold alloy with the addition of 20 ppm of iridium. And so this hypothesis explains both the refinement of the grain size and the presence of twin boundaries. Moreover, this microstructure have been this hypothesis has been also involved to explain peculiar microstructure in materials processed by additive manufacturing, such as the Nitonel 718 processed by DoD, where one can see areas where fine grains and a lot of twin boundaries, plotted in black, plotted in white, and also in the nickel processed by L-PBF, where one can see a lot of twin boundaries, plotted in red. So this hypothesis seems attractive to explain the microstructure we observe, and we will explain it. So to present the icosahedral short-range order, it comes from an icosahedron, which is a solid with 20 faces and 12 vertices, where each face is an equilateral triangle. So an icosahedron is a compact order that atoms can take in the liquid, as suggested by Frank Casper. But this presence has been also shown by XRD in the liquid and also modeled by ab initio calculation. And it is well studied because it is the basis of all quasi-crystal studies. So what is known from the literature is the liquid can be organized locally in the form of chains of icosahedron. So the hypothesis of IS0 mediated nucleation is the nucleation of an FCC crystal on an icosahedral template. And because there is a special orientation relationship between FCC grains and the icosahedron, it creates a special orientation relationship between nearest neighbor grains, such as twin boundary and 110 common direction. To validate this hypothesis, what is done in the literature is trying to find the orientation relationship expected with this hypothesis. So this is what we've done. And we identify a cluster in the Praxair steel. So here we define a cluster as a set of grains that are all related by twin boundaries. So we pick up a cluster of 13 different grains. And we analyze the orientation relationship between the grain of this cluster. And we found 6-5-4 symmetry, as one can see on this core figure, which corresponds perfectly to the 5-4 symmetry of the icosahedron. So we were able to put 10 grains of the cluster on an hypothetic icosahedron germ. So here we obtain an important clue, because this 6-5-4 symmetry is very unlikely to appear by random twinning. So we obtain an important clue that the IS0 mediated nucleation mechanism is present in the material. But we also think that the IS0 have an impact on the nucleation of grain, but also on the growth of them. And we think that by superimpose the main pole boundaries and the cluster. So this is what we've done on this image, where we can see on the grain boundary map that we highlight the cluster. So there is nucleation of this cluster in the main pole below. It grows over several main poles, and then there is twinning 3 melting pool above. And this is difficult to explain by the hypothesis of IS0 mediated nucleation. And that shows that IS0 could impact the growth of grains. These hypotheses have been developed in the literature as the mechanism of ISRO-induced statin fault, where one can imagine that the ISRO modifies the genetic attachment of the atoms on the dendrite. And so one can imagine an icosahedral will attach on the solid cells, and this will create twin boundaries. Okay, now we think that the ISRO is likely to modify the microstructure. But why there is a difference between the SLM steel and the Praxair steel? What composition element gives this mechanism of ISRO? To try to see what element is responsible, we compute several papers where we think ISRO modifies the microstructure, such as the one presented here in a 304L processed by L-PBF, where one can see a lot of twin boundaries in their half-fabricated steels. And so we suppose that the origin of their twin boundary is the same as the origin of the twin boundary we studied. We found 4 papers in 316L, and 2 papers in 404L, where the ISRO seems to modify the microstructure. And we try to find a common point with all the composition we found. And the only correlation we were able to make were with the nitrogen content. We found that all the microstructure where ISRO seems to have an impact have a low nitrogen content, less than 400 ppm, as you can see on this graph in red, while all the microstructure without ISRO in blue, so this is classic microstructure with large grain, one can see that there is always a high content of nitrogen above 400 ppm. So we were able to make a correlation between the low nitrogen content and the impact of ISRO, and this was the only correlation we were able to make. So as a conclusion, we saw that the microstructure of 316L processed by L-PBF can be very sensitive to the initial composition, and that ISRO is likely to cause the microstructure change in the case we study. We show also that the nitrogens seems to inhibit the ISRO, but this needs further investigation. And because we show that the ISRO seems to decrease the texture intensity, and that we know that the texture can be a problem in additive manufacturing, we can wonder if the ISRO can be used as an alloy design to eliminate the texture effect. So thank you very much for your attention. And do you have any questions?